Good morning and good afternoon, everyone. Welcome to today's webcast, Optimizing CEMS with Emerson's Hot Wet Sampling Solutions. I'm Lauren Murray, Global Integrated Marketing Manager for Emerson's measurement instrumentation business, supporting our gas analysis, engineered solutions, and lifecycle services portfolio, and I'll be your moderator today. Accurate real-time gas analysis starts with one thing, representative sampling, and without it, even the most advanced analyzers can't deliver the insight you need. In this session, we'll spotlight why Emerson's CEMS solutions for hot-wet measurements enhance accuracy, compliance, and efficiency across several challenging environments through our hot-wet sampling. Joining us for today's webcast are Sarah Calhoun, PGA and QCL Business Development Manager, and Keith Lindsley, Senior Global Product Manager from Emerson. Sarah Calhoun manages business development for our Rosemount process gas and quantum cascade analyzer product lines. She brings over a decade of analytical experience in petroleum and specialty chemicals and holds a PhD in analytical chemistry from North Carolina State University. Keith Lindsley has nearly 30 years of expertise in process analytical systems integration. As Senior Global Product Manager, he's led projects worldwide across industries like power and petroleum. Keith holds a bachelor's degree in mechanical engineering from Purdue University. Before we dive in, let's go over a few quick housekeeping notes. So following the presentation from Sarah and Keith, we'll have a Q&A session, and you can submit questions anytime using the Q&A box at the bottom right of your screen. Additionally, you can resize or move widgets on your screen and maximize the slide view by clicking the arrows in the top right corner. Lastly, if you run into any technical issues viewing today's event, please press F5 to refresh your screen. So with that, we'll get started. Keith, I'll hand it over to you.
Great, thank you, Lauren. Sarah and I are very happy to be here today to discuss the advantages of hot-wet sample analysis in sampling design and good practice considerations. As most of you on the call know, hot-wet sample technology has been available for well over 50 years with process gas analyzers such as gas chromatographs, mass spectrometers, and other analyzer technologies. CEMS applications have mostly been handled with dry systems and dilution systems to date, but with the advances within our QCL, the ability to measure moisture in real time, let alone the other hard to measure components, there are many applications where measuring hot-wet is not only preferred, but technically superior to traditional cold, dry moisture removal systems. We realize that 60 minutes is not an abundance of time here, so we welcome you to reach out to us individually sometime after. Sarah's going to kick us off here, going into the details of quantum cascade laser spectroscopy, and then following that, I'll get into some of those sample design considerations. So, Sarah, let's get started.
Sounds great. So here we've got our suite of QCL analyzers. Today we're talking specifically about the 5800, 5100, which is our premier analyzer for hot-wet. We have the 5800, which we use for trace analysis, and the 5400, which is a rack mount version that's also available for hot-wet analysis. Our 4400 is cold dry. I'm going to speak specifically on the technical aspects of using direct absorption spectroscopy, which is going to be the same technology that you find within any of these analyzers in the QCL family. So specifically, if we look at the advantages of the 5800, we've got a really reproducible measurement. We'll look at exactly what it means to be doing direct absorption spectroscopy. There's no modeling associated with this because we're looking at how these molecules are absorbing energy. There's low maintenance. Unlike a GC, you're not going to have any sample injection valves, so a lot less moving parts. No chopper motors that you would have with your traditional UV or IR measurements, and no chiller since we can run this as a hot-wet measurement. We can measure ammonia directly, or we can measure around it, so there's no need to have an ammonia scrubber, which just takes out a lot of complications with your sample system to lower that maintenance. As far as cost of operation goes, you've not got any gases that are running through it like you would have with a GC, and our mean time to failure on our lasers is greater than 10 years. So there's not really any consumables that you're going to have to change out. We're going to be measuring NO and NO2 if that's something you're interested in directly. So there's no ozone generator, no conversion that's going on, because we're going to use that direct absorption spectroscopy to look at those molecules. It's a pretty cost-effective approach because we've got the ability to measure with 6 different lasers, so we can have at least 6 analytes. Sometimes we can get a couple analytes off of a single laser. So rather than having 2 or 3 analyzers in a shelter, you can have 1 analyzer, and we don't actually need a shelter. So Keith will talk about sample systems and applications more. From a cost perspective, if you're looking at a new application, shelters are a big part of that cost, but there's also a safety component there. Anytime you can keep an analyzer out of an enclosed space in a more freely ventilated place, that's probably going to be a safer route, just so that you don't have gas buildup. Because there's a lot less maintenance items here, we have high uptimes, which keeps regulators happy and plant managers and technicians, right? So eliminating your high hitters with your maintenance items helps us to achieve really high availability. And we'll look at how quickly we're taking measurements. We're going to look at how we make 1,000 measurements per second, but that means for you as an end user, you're going to get an update every second for each analyte that you're looking at. We're doing this all in a high temperature hot box on top of the analyzer, as you can see over here on the right, up to 190 C. So let's look a little bit more in depth at the spectroscopic component of this. Anytime you've got wavelength coming into a molecule, you're going to get different types of absorption. And this is very specific per analyte. So if you have a carbon that's connected to 4 other hydrogens, like methane, versus something that's got another carbon, they're going to absorb in a very different way. So your spectra for each analyte is kind of like its fingerprint. We get to use both the near IR and mid IR range. So our traditional TDL technology is only up to about 2,500 nanometers, whereas with the QCL technology, we can go a lot farther, and this enables us to get to a lot of different types of molecules. So specifically, this is kind of like some of our most common analytes that we look at. So O2 would be a very typical thing that we would look at in the TDL region. And because we've got the ability to go up to the higher wavelengths with our mid-IR region, we can get to a lot of different molecules that are not as accessible in that lower near IR range. Today, we're going to look specifically at moisture and ammonia. So those two are something that we can measure together. And one thing to note is that all analytes, usually they're going to absorb in multiple regions. So just because you have a single analyte that on your analyzer, it gives you one reading, that doesn't mean that that's the only place that it absorbs in the spectra. So let's take a deeper look at both moisture, water, and ammonia. Each of these analytes, so water is going to absorb throughout the spectral region. So this is the spectral fingerprint for water here on the left. On the right, we've got ammonia in red. So we can see that there's a lot of different places throughout the spectra that we get absorption for these molecules. Depending on what you're looking for, if you're looking at ppm level moisture, or if you're looking at 50% moisture, we'll pick a different peak based on what you're looking for. So obviously the lower the concentration region you're looking for, we're going to look for a part of your spectra that has a high absorbance region. If you're looking at a high percent level, we don't want to overwhelm our detector. So we're going to pick one of those peaks that has lower absorbance so that we can tailor the measurement to be quantifiable in the range that you care about. The other thing we have to look at is where they interfere with each other. So we can see that there's several regions with ammonia and water where you're going to have absorption of both of those molecules. So what we would do is find regions within the spectra that don't interfere with each other. So whenever you submit your application data sheet, we ask for everything that's in your stream and what you want to quantitate. And this is what our application team does for you. Before we send you the quote is we actually pull up and look at all the places that we're going to have absorbance from all the different molecules. So you can see down here in the 2000 region, we don't have a lot of absorption from water. So that'd be an ideal place for us to quantitate ammonia. And up here in the 12,000 region, we've got not a lot of absorption from ammonia. So that'd be an ideal place for us to quantitate water. So this is the kind of thing that we run through for each application to figure out how the best way to make your measurement would be. So because we're using direct absorbance, we're going to be taking 1,000 samples per second. And then we're looking at the shape of those peaks and looking at the area underneath there to be able to quantitate how much of that species is there. The more analyte that's there, the more light is going to be absorbed, and that's how we are able to quantitate. You can zero and span this just like you would a GC or most of your analytes on site. You have the ability to calibrate it based on the peak absorption. So why do we call it the quantum cascade laser? This actually comes from the laser. As you heat up the laser, as the electrons enter into the quantum well, you're going to get an electron transition, which is going to emit a photon, and that electron is going to continue to tunnel down to the next well. Those photons that are emitted from each well are at a extremely small but different wavelength. So we're actually sweeping through a couple wave numbers, 2 or 3 wave numbers in the spectra to get that small region like we pulled out to look for the peaks that we've decided to quantitate your application off of. So if you have something like ammonia there, it's going to absorb part of the light from those photons that are emitted from the laser, sweeping through those wave numbers that we've predetermined. So we power up that laser, that heat that actually heats up the laser. We sweep through a few of those frequencies. Your analyte of interest absorbs there. And then we use a Peltier cooler that cools the laser back down. And we're able to do that with that sweep in 500 nanoseconds, and we'll move on to the next laser in about 1 millisecond. So that's how we're able to get so many readings out of the analyzer per second. This is an advantage from an analytical perspective. We've got a lot of spectra that we can use. So our algorithms are able to use that. And that's part of the reason we're able to have that low limit of detection and that reproducibility. So just the physics of the laser help us to not have much drift. Just a really reproducible and quick measurement that gives us that 1 second refresh rate on all 6 analytes that you could choose from with the lasers. So here, you can see up top here, we have our different laser cartridges. So each one of those is going to be a chosen laser for a specific analyte. We're going to be looking at a really small part of that spectra for each analyte. Then the lasers actually use the same path length. So you're going to have one laser chirp, and then the next laser will chirp. So this is going to happen, and it goes through the same path for each laser. It goes through the cell down here and bounces back and forth between the mirrors before it goes out to the detector. So this is really the other place that we have opportunity to tailor this to your measurement. So we can do different path lengths, 5 meters up to 15 meters, depending on if you're looking at that ppm or percent level measurement. We have both the spectra and the path length of the cell that we can use to make sure that we're giving you the best analytical approach possible. So this is my last bit of theoretical spectroscopic information for you. A disclaimer that not all spectroscopy is created equal. So you can see here we have the spectra for both the QCL and something like an NDI or FTIR. So with those approaches, you're going to have modeling, but the fundamental vibrations and things can be different there. And a lot of times you've got broader peaks. So one of the real strengths here from an analytical perspective is that we're doing direct absorption spectroscopy. We've got really sharp peaks and we've got several peaks to pick from. So with that, I'm happy to hand it back over to Keith so he can give us some more details about different applications and how they relate to regulation.
Great, thanks, Sarah. So just really quick here, as Sarah told you, she is very much focused, laser focused on the product part of the business here. I'm in what we call the measurement systems and solutions group. So we are basically the integration arm of Emerson. So just a quick note on that, we've got 500-600 employees all over the world. We have thousands of systems also all over the world within liquid and gas phase, process, analytical, and then CEMS, process analytical CEMS, which is mostly what we're talking about here today. So big criteria here, and most of you on the call probably know what's the difference between cold dry CEMS and hot wet CEMS. So cold dry, just like it sounds, we are taking all the moisture out of the sample. So the sample gas is coming out of the smokestack, staying heated from the stack all the way down to the sample system to the analyzer. But at some point, all that moisture is being removed. So the analyzers for those types of systems, they're not hot. They are under ambient conditions. So therefore, they can't measure moisture. And moisture in the analyzer would be a bad thing. So messing up pumps, mirrors, et cetera. So most of us on the call, if we're familiar with CEMS, probably have many of these cold dry systems. So hot wet, again, just as the name implies, we are keeping that sample hot. So by keeping the sample hot from the probe tip all the way to the analyzer, we are actually able to measure the moisture, well up to 25-30% by volume of that sample gas. And then in addition to being able to measure moisture, we can measure some of those other very difficult measurements that get scrubbed out when we're measuring, when we take out the moisture, like HCl, like ammonia, like H2S. We're often measuring those in such low ppms that any moisture removal system would take sample out as well. So hot, wet, cold, dry. Really quick here, just an example of some hot, wet systems. The one on the left here, this is actually a full system. This is actually a full system of what a gas turbine application would look like out in the field without a shelter. Would not need a shelter necessarily. We could put that in a cabinet. So rack version of a hot, wet system. Here in the middle, top middle, just a picture of a full-blown shelter. So the hot, wet sample system on the outside, the analyzer on the inside. Again, here's that CT5100 mounted in a rack here. You can notice that's gravel out here, so that's somewhere out in the unit. And then this third picture on the right, again, I call this a bus stop. So this will just be out in an area, no HVAC, protected from rain. So much lower cost, going this direction as opposed to full shelter. So sampling challenges with traditional cold dry. So we've already established there's some things that just can't be measured cold dry. We're removing the very thing that we're trying to measure. So on top of that, though, we are adding extra components to maintain a system. So we are adding gas conditioners, we're adding chillers. We might be installing extra moisture filters. We might be adding extra moisture sensors, closed contact sensors, which would mean additional pumps, peristaltic pumps, extra tubing. So all of those items, it doesn't seem like a lot, but it does create more maintenance. So if we are doing maintenance on a quarterly basis, if we are doing maintenance on just an annual basis, those are certainly more points to have to account for. And if you're a bigger facility, have 12 analyzer systems as opposed to one, those hours do add up. So one of the first considerations when we're designing our system is, what's the application? What are we measuring? And I've got some application slides here at the end. But the number one, there is no number one, but on this slide there's a first. So the material consideration. So if we are staying hot, Teflon is obviously not going to be an option in a lot of cases because that Teflon will be getting so soft that under pressure or under vacuum, we could be losing the seal of those Teflon ferrules, of that stainless steel Teflon ferrule. The Teflon gets too soft. So, so hot, wet systems, if we're really going above 260, 270F, would not want to use Teflon. If we're measuring ammonia or HCl or some other components, we would not want to use just normal stainless steel either. So if you looked at quarter-inch stainless steel tubing under a microscope, that tubing really looks like the crater of the moon. Just the surface of the moon. There's little craters everywhere. So we would want to do silk inert. At minimum, we would want to do silk inert polished tubing. So that's a glass coating, rough out those craters. But often just that's not enough. So then we might have to use Hastelloy, might have to use Inconel, Monel, etc. So especially the application and what we're measuring, the temperatures, all will account on which materials we are going to consider. And then on top of the materials, things that people don't often think about, our components within the sample systems are also rated to temperature. So the electronics, the wiring, the terminal block, the flow meters, the rotometers, they all have limitations on heat, much less pressure. We know that. But I have seen systems where the temperature limitations haven't been thought through, and we've used, not we, but some have used the wrong temperature rated rotometers in sample systems. So have to consider that. This one's really important to me, hence the exclamation point there. So dew point temperature, I feel like we're really eager to prove that we know all we do about dew point temperatures in the stack. But the problem with dew point is that stack dew point does not translate to what the dew point is when it enters your system. So as we are coming, 100 feet, 200 feet through a sample system, and we are, going through swage lock or Parker fittings, our orifices are expanding, they're contracting, we're bending, we are transitioning from vacuum phase to vacuum phase, pressure phase to vacuum phase. We really don't know what that dew point is, the whole chain, all the way across. So this is very easy. I would always advise people, don't worry about your dew point, just keep it hot. What are you measuring? What are some of your background gases? Get that temperature above the point where ammonia salts will form in your probe, in your filters, and that will suffice. And then, of course, you'll have to do maintenance from time to time, to account for, any issues with that. But you're not going to have moisture. You're not going to have moisture breakthrough. Most importantly, we're not going to have water in vapor or water in liquid form enter the analyzer. So again, keep it hot. Minimum 120C, as high as 190C. So some of the values here, one of the biggest values, as we've said so far, is being able to measure moisture. So we're keeping it in vapor phase. The analyzer is actually measuring that water vapor. Well, what can we do with that water? And many of you in CEMS, you know this answer already. If we have a flow rate analyzer with our CEMS, we're having to convert those ppms to an emission rate. We're having to transfer those ppms to pound per hour. And a lot of analyzers are measuring the ppms in dry ppm, but all flow analyzers are actually measuring in wet, on a wet volume basis. So you're that measurement is of velocity of delta P. It's happening in wet standards. So we have to convert one. We have to either convert wet ppm to dry ppm, or vice versa, so that we're multiplying the wet ppm times a wet flow to get a true pound per hour. So with that, we don't need a additional moisture analyzer. One, if that were so important to us, we wouldn't need an additional moisture analyzer to measure that moisture. Two, we would not be relying on a once a year determined K factor during the RADA and use that straight water number the entire year. Just with every measurement, just as ppms go up and down, my moisture number would go up and down. So much more accurate. So being able to know exactly what my dry and wet ppm are going to be, what they are, having a real handle on what my true emission rate in pound per hour, very important. And ironically, what you're looking at the screen there is an EPA method 1 through 4, 1 through 5 sampling train. This is the methodology that would that validates, certifies our moisture system on a once a year basis. The analyzer is probably 100 times more accurate than an Impinger system. So this is how we meet that compliance. So next item, NO2. So a lot of you on the call, if you either have a CEMS, if you are someday going to have a CEMS, you might have a NOx measurement. And 99% of all the NOx measurements in the world do not measure NO2. Most of them are chemiluminescent systems where we are taking the NO2 and in some way, shape, or form, we're converting that NO2 to NO, measuring that number again, and then we're getting what we call a differential NOx number. So a couple things with that. We as end users, we as an OEM, if we are installing a chemiluminescent-based system, we're required to test out that NO2 converter, test out that NO2 efficiency test once a quarter, once a year, and so forth. It's not a hard task, but it takes time. I don't think those NO2 calibrations and that maintenance is happening as often as it should. So if we're actually measuring the NO2, one, we're going to really know what our NOx is. We're not converting NO2 and hoping that we convert it at all, and we've eliminated an awful lot of maintenance on that NO2 conversion test. So when our state regulator says, can we look at the NO2 conversion records? You're not going to need them because you're calibrating every day. You're calibrating every day within NO2 calibration gas. So, and then the built-in air. So, on the conversion side, on the test side, both have a plus or minus 10% error. So a lot of potential error in all of that NO2 converter application, much easier to just measure the NO2. So with that, what applications are ideal for hot wet analysis? So just a few here: gas turbines, everything in petrochemical, pulp and paper, cement, waste to energy. So let's start with Part 75 CEMS here. I'm not sure if we have any gas turbine operators here, but within the regulation, there's very tight regulations for NOx. There's very tight regulations for CO. The relative accuracy requirements under Part 75 are not half, but an annual successful RADA is 7.5% as opposed to 10 or 15% on the Part 60 side. So we have to be accurate, 7.5% on the RADA, 0 to 0 to 20 ppm range for the CO and the NOx, but also often for the ammonia. And this is where the technology really becomes important. So there aren't very few, very few analyzers that can also measure ammonia in a extractive basis the way we do it. So those ammonia numbers, they're going to be below 5 ppm. So of course we have to measure that on a hot wet basis. We cannot use a chiller that would pull out that ammonia. And then again, we're doing it on extractive basis, so we can actually calibrate, validate, zero the analyzer. Many ammonia systems within Part 75, they're actually in situ. They're using cross-stack lasers up on the stack, so it's a completely different system, and you're not actually able to completely zero, completely zero the system. They call them bump tests, they call them dynamic spikes. So we are actually, again, completely able to measure the ammonia with all the other traditional stack gases in a single analyzer. So very important. And then with that, we have our Emerson developed EPA Part 75 data acquisition to go into that turbine market. So next application, petrochemical. One thing to note, Rosemount, Emerson, we have always built our analyzers to be both general purpose and hazardous area. So, so the CT5100 is no different. We can go into the refinery, which as we know are quite keen on using Class 1 Div 2 equipment overall whenever we can. So we can put our Class 1 Div 2 analyzer in, we can put our Class 1 Div 2 sample system in. We don't need a shelter, so we can save that real estate within the refinery. I've been asked a million times over the years by plant managers, by refinery managers, when can we make these systems smaller so we don't have to have all these shelters and all the maintenance items that go along with it, and safety considerations. So, so again, analyzer sample system can be open rack. We can put them in a Class 1 Div 2 enclosure with an HVAC. And of course, we can go into a full shelter like you saw on one of those opening slides. So units of the refinery, so ideal for the FCC stack where we're measuring everything. We're measuring the SO2, we're measuring the CO. We, depending on the refinery and that application, depending on the crude coming in, they might want to measure H2S at that stack there. Might not be compliance, but it would be a good item to have there to know, to speciate those sulfurs, very possible. Process heaters, not as many measurements, but ideal for the process heaters, sulfur recovery units. So all of the applications, we can cover all of the applications within the refinery there. We also have a hydrocarbon laser module, so we can measure those hydrocarbons as opposed to a FID or a GC. Depending on the application, we can use the hydrocarbon laser module. And again, refineries are Part 60, so this would use our Part 60 Emerson data acquisition system. So pulp and paper. Anybody on the call here in the pulp and paper industry, you could tell this to all of us. That this analysis has been being done the same for 25 years. So total reduced sulfur, that is the hard measurement here. So basically what they've always done is they've had two sulfur analyzers end to end. They're running the sample gas through one analyzer. We have an oxidizer. We're heating that sample then up to 650, 700 C in between the two analyzers, and then we're measuring that gas again. So by oxidizing the stack gas a second time, we're now able to measure, we're converting the TRS compounds, H2S, dimethyl sulfide, the methyl captains, we're converting that back to SO2 and we're measuring again. So one, we have two analyzers. Two, again, there's this conversion operation that we have to do to make sure that we're efficiently converting all the TRS to SO2. More maintenance is supposed to be done and documented every quarter. So if we are actually measuring the TRS components, all of the conversion, maintenance, and reporting goes away. Depending on the mill operator, depending on the application, I could see some mills actually wanting to know that speciated data. They would love to know the percentage of their TRS that is H2S as opposed to all the other compounds. Or I could see them say, no, I really don't want to know that. I just want the total TRS number. So both are possible. But having control of what you measure, having control of that available speciation, I do think that's important. So again, this would plug into a Emerson Part 60 data acquisition. Back to the sample system on this, the heat is important, but the materials are more important here. Paper mills, often very nasty applications, very corrosive. So we probably would not just do silicon earth here. We would have all the materials from probe tip to analyzer inlet be Hastelloy or maybe even something else. So definitely have to consider all of our swage lock Parker fitting components here. Another tricky one is cement. So burning garbage, waste to energy. So most of the measurements here are traditional, our NOx, our CO, our SO2. But many of the incinerators have an HCl limit as well. An HCl limit, you have to report it. So again, we could add the HCl channel, HCl module to this analyzer to measure the HCl with all the other components. And again, doing it with the same analyzer, we are running the sample gas through the entire system. So we are calibrating the entire system just like we do with every other stack gas. So the heat is very important, keeping that HCl hot so it doesn't condense out. We don't want any acid on the mirrors of our analyzer. And then again, all the components from probe tip all the way to analyzer inlet, we want to make sure that it is going to not corrode. Some of these cement, some of the I got my slides backwards. Apologies here. I was talking hazardous waste cement here, but both are the same. It would go through the stainless steel fairly quickly here. So definitely have to make sure we're using the right materials for cement and incineration. So here's the waste to energy here. So again, very similar to the cement. We're measuring the SO2, the CO, and the NOx. They often require that HCl. So again, we're actually measuring the HCl with the analyzer. We're calibrating. We're doing the linearity through the whole system. One question I often get asked here, can we do dioxins and furans? Can we do polyaromatic hydrocarbons? Unfortunately, we cannot do that. So would love to someday to be able to do the PCDDs and dioxin in a single analyzer, but we do not do that. So, but all the other traditional CEMS measurements, the HCl, all within the confines of the single analyzer. So doubtful we have any stack testers on the call here, but if we did, again, this is an ideal analyzer for the stack testers. This is a true multi-gas analyzer. A lot of multi-gas analyzers, they're using one laser, you're using one detector to make all the measurements. And one type of spectroscopy is not ideal all the time. One detector, one laser is not ideal all the time for all the different things we can measure for all the different ranges. So they have to employ chemometrics, they have to employ some modeling to make those numbers work. So our solution, with possibly two detectors, one for the tunable diode laser portion and the QCL, and 6 different laser modules, we can tune those laser modules very specifically to what we're measuring. Only 2 measurements per laser. So very, very accurate. So as a stack tester, a very good analyzer to come in and only use one analyzer as opposed to bringing 4 or 5 different types of analyzers. Again, with the multi-gas analyzers, and like with flow, we've all heard of K factors, we've heard of X factors to account for the variability. So we do not have to use any type of K factor or X factor to change our output, to change our values depending on what type of fuel we're burning and so forth. So it's all within that measurement and detection analysis. So just to kind of go back over the application again. So we are very well suited for field mounting as opposed to traditional, as opposed to the, my slides are jumping on me here. Very able to be field mountable, in the rack, out in the open, from -20°C up to +50°C, as opposed to having to put in a cabinet or put into a full-blown shelter. And again, all of our analyzers are Class 1 Div 2, so if we were going into a Class 1 Div 2 setting, we would make all of the sample system requirements around it, also Class 1 Div 2. So again, our analyzer, it's actually, we say QCL, first always, just because that is the leading technology, but these analyzers are both quantum cascade laser and tunable diode laser. So both technologies in the same analyzer. So my slides are jumping all over without me here. So, and again, we offer both EPA Part 60 and Part 75 data acquisition systems. So, so less buyouts. So again, from the integrator part of the company here, less buyouts. So we control the analyzer. We do all of our own integration, all of our own the engineering, and then our own data acquisition. So it is just about 45 minutes through this. I see we have an awful lot of questions. So good place for me to stop here. The slides already told me to. So good place for me to stop and dive into questions.
Awesome. Thank you so much, Keith, for that. Yes, sometimes when we do these webinars, we have a little bit of technical difficulties, but that's okay because we will prevail through. So we do have quite a bit of questions over in the chat. So the first one that someone would like to ask is, okay, so paramagnetic type is used or not used in our analyzers to have O2 measurement for normalizing the parameters as per guidelines. So I think they're asking, are we using paramagnetic types or not?
Sarah, I'm going to let you, from an analyzer standpoint, if you would grab this one.
Yeah, sounds good. We have that technology in our traditional PGA analyzers. For the hot-wet measurement, we need to use the TDL laser approach. So we're using the TDL laser instead of the paramagnetic oxygen, just because that moisture can play a role when you're looking at the magnetism of oxygen. So that dumbbell is going to be affected by moisture. So the laser is a much more robust approach for this hot wet. So that's what we're doing, is that TDL laser.
And then just, I'm looking right at it here, Pugazendi, on that question, I can see your question here, talking about the 6 laser modules. So one of Sarah's slides, and you can go back and rewatch this webinar, one of Sarah's slides showed exactly which components are measured with QCL, which are measured with TDL. The oxygen is measured with TDL. So, so majority of the compounds we're measuring are done on the QCL side. And then just on that, just because the QCL can measure more things, it usually is a configuration of 5 QCL lasers, 1 TDL, but it wouldn't have to be that way. We might be in a situation where we've got 4 QCL and 2 TDL. So really application dependent.
Okay. Next question. Do the lasers account for ductwork expansion?
Great question. And I love this question because a lot of the other ways to measure what we're measuring are in situ lasers. In situ lasers, we're going cross stack. It might be 10 feet, it might be 30 feet within the sun, within the heat. The stack, the ductwork is torquing, right? So that metal is shifting all over the place. And when they lose laser alignment, well, once we lose laser alignment, we're no longer measuring anything. So we are completely pulling the sample out of the stack. So no, when that port torques, when there's movement in the superstructure of the stack there, and that probe has no bearing on what we're measuring whatsoever. So we are pulling that sample intact all the way down to our analyzer. So great question. Thank you.
Hey, a follow-up to that, they would also be interested in how often our solution would need to be calibrated.
So calibration validation. So EPA CEMS, you validate every day. The way I set my systems up, that validation is going to run at 6 o'clock in the morning before you get to the plant. When you get to the plant, the validation is done. It's all going to pass. And if it didn't pass, if one of them did drift, now you're going to rerun your validation again. And if you have to change something on the analyzer, then you would calibrate. Now you're manually zeroing or manually spanning the analyzer to change the calibration. So validation daily, calibration very, laser, laser technology, all laser technologies, there's little drift. So very little chance of having to recalibrate. I see an SCR question here as well, selective catalytic reduction. Lauren, if you could touch that one.
Of course. Okay, so we are designing a simple cycle plant and are required to have an SCR. We're planning on adding ports to our inlet ductwork on the SCR duct. So my question is on port placement. At what elevation should ports for this system be installed, and what is the diameter size of these ports?
So I'll start with diameter size. So the ports are going to be similar to all types of gas analysis stack testing ports. So a 2-inch inner diameter would be fine. In some of these SCRs and some of these air heater inlets and outlets, the ports are really long. Sometimes they're 4 feet long, 5 foot long. So if you have really long ports, just to make it easier to get ports in and out, I would make the probes in and out. I would make those ports larger. So anywhere from 2 inches to 4 inches in diameter. So as far as placement goes, so downstream, upstream disturbances. So at the inlet and the stack, the farther you are from downstream disturbances, upstream disturbances, the better. Ideally, those numbers are 8 and 2, 8 diameters or 8 equivalent diameters downstream from disturbance. That means a reduction in the area of the duct or pipe or a bend. So 2 is the minimum. Actually, probably 1 is the minimum, but 8 is ideal. And then on the downstream side, sorry, that was the upstream. Downstream flow rate after the port, 2 is ideal. So that would be the stack exit or another bend or another ductwork reduction there or expansion. So 8 and 2 is ideal. 1.5 diameter, 1.5 equivalent diameter, and 0.5. That's kind of the minimum, but you have what you have. So more is better.
So this next question is going to be more related to service, it looks like. So how many service technicians are available for the QCL products right now?
No, great question. So this technology, so Cascade Technology, it was a company that's been around, over 20 years, over 30 years, Scottish-based company. We purchased Emerson purchased them in 2014. We had our first North American service training here at our Pasadena field office in Texas, first week of June. So we brought in 9 of our technicians that are already familiar with other types of technologies, the GCs, some of our pressure, temperature, flow equipment, our PGA equipment. We brought some of those folks in and got them cross-trained on the Cascade technology. So, and I was part of that training. Sarah was part of that training. We know these people individually. We have 9 very qualified technicians at the moment, and that will continue. So Houston is one of our 5 global service hubs. So that number will be ever expanding.
Okay, do you see a range where you start having problems with too much ammonia in the process?
So those are 2 questions here. Sarah, I've done all the talking. Do you want to take this one? I'm happy to, but I've been hogging this.
So the 5100, we've got the lower range. We can get down to 0 to 10 ppm, and we've had some applications up to about 1,000. I don't know that I've seen many above that. I'm sure there is a point where you would have too much ammonia, but I don't know that we've run into that yet. Anybody that's got an application. So if you have something specific in mind, I'd love to put together an ADS and we can talk to air folks and see if we can make an application for you.
In listening to that question, I can see more problems with high ammonia being on the process side than on the analyzer side. So, no, the high ammonia capability there will definitely indicate when you are going to have a problem on the process side from those huge ammonia numbers.
All right, another application question. It looks like, can you all speak to why coal, LDO, or HFO fired thermal power projects are not in the list of applications for hot wet analysis?
I sure can. Anybody in Part 75 CEMS, particularly coal-fired units, dilution CEMS has been the standard for quite a long time, and they do a really good job. The companies that do those types of systems have dilution analyzers. They have ppb type analyzers. Their low range is 0 to 50 ppb. Those analyzers were meant to measure ambient air, and so they took ambient air analyzers and repurposed them within the stacks, within smokestacks. So why is this helpful? They are diluting that stack gas 100 to 1, 250 to 1, so as to not have different types of sample analysis problems, not analysis problems, sample handling problems. The maintenance items are different, but bottom line, with all the particulate in coal, by diluting, they've changed their sample system maintenance. So it is a good technology. We do not have PPB technology, so it's just not an area that, admittedly, we don't do the coal-fired boilers as effectively as dilution systems.
All right. So what documentation is available for installation procedure and port sizing and location? And are those drawings obtainable?
Yes. These are all very standard. So if somebody can reach out to me, Keith.Lindsley at Emerson.com, more than happy to get you those, get you that detail.
Okay, perfect. So we have time for a few more questions. So we'll read off a couple more. How do you validate the moisture percentage from the QCL?
Sure. So, again, any customer that has a volumetric flow rate system, they're having to report their CO or their NOx on a pound per hour basis. They're doing that RADA once a year. They're doing the relative accuracy test audit on their analyzers. They are also doing that relative accuracy test audit on their flow system. Part of the test on the flow system is measuring moisture. So we're measuring velocity, we're measuring moisture, we're using that data to convert to volumetric flow. So if it's a power plant, if it's a Part 75 application, over 2 to 3 days, they're doing 36 moisture runs against our analyzer. So we are showing accuracy during that RADA period. If it's a Part 60 system, we're only doing 12 runs. But again, we're using our moisture number versus the stack tester's moisture number, validating the number, and then using that number the whole year, or proving that our accuracy is good for the whole year. So with the stack test, with the EPA method 1 through 4 test methodology.
This looks like this next question may be for Sarah. So of 1 TDL and 5 QCL, TDL measures which gas?
So I think the most common gas that we measure with TDL is oxygen. But we have HCl and HF that are also in that TDL range. It kind of just depends on your application and how that analyte absorbs light. So it's just dependent mostly on what all's in your stream.
Okay. All right. Next question. Is there any specific air permit requirement? So why VOC measurement part regulation? Is there any specific air permit requirement?
So let's start from the top down. So EPA writes regulation. The regulations apply to all 50 states. Every state can come in and write tighter regulation. They can't go less stringent, but they can go tighter. And then some parts of the country, like California, some parts, other parts of the country, where local areas, counties, or greater city areas, they can even have different permit requirements. So, so long answer to this: the permit defines what is needed. So, and the permit is written at the local level. So the permit's written based on the federal regulation and then the state regulation. But whatever the permit says, that is the go by. That is what we follow.
All right. What is the maximum temperature handled by the laser measuring cell? Sorry.
Our cell 190. Yep. I'm sorry, 190? Sarah, I was waiting for you. But yeah, it's 190. And let me just clarify something on that real quick. So we can go hotter on the sample system, leading up to the analyzer. The analyzer itself has very low volume. The Harriet cell within the analyzer is very low volume. So we could actually be running our gas temperature 230, 220, 233 right into the analyzer. We then would be dropping that temperature to 190, very short path length until it leaves the analyzer. So, so 220, 230 C in the sample system, probe all the way down, but then we would stabilize at 190 within the QCL.
The other thing to think about with that is that we're going to be under a vacuum. So if you're looking at dew point, you like Keith talked about, it's different all the way throughout that system, but in that cell, you're going to be in a vacuum at 190, which will help you stay in that gas phase.
Okay. All right, so we'll make this one our last question of the day. Does Emerson have an EPA data acquisition system?
We do. Yep, we are doing FATs as we speak. So we have a Part 60 solution, and then we have a Part 75 solution. Someone asked earlier about the coal-fired units. So so to be clear, when we do our Part 75 systems, we are talking anything but coal. So we would do the waste to energy. Certainly, we love the gas turbine applications, oil. So we would do anything over 25 megawatts. That would be a Part 75 application that we have a solution for.
Excellent. All right. Well, thank you, Keith, and thank you, Sarah. That concludes today's events, and we hope that you all learned something new. For additional viewing, this webinar will be available on demand on our Emerson video library and then also on YouTube, and it will be emailed to you afterwards as well. Again, if you have any questions about any of our products, solutions, or services, please don't hesitate to reach out to either Sarah or Keith, either via their email, which is going to be their first name last name @emerson.com, or via their LinkedIn profiles, which you can access on the homepage on the left side of the screen. And then additionally, you can also visit emerson.com as well. So thank you again, everyone, and have a great rest of your day. Bye.
Thanks for your time and the questions.
Thank you, everybody.